All right, in this session we're going to be looking at the steady state error, and in particular both at analog control systems and also digital systems. We're going to find that the steady state error is a measure of the difference between the input and output signals for a prescribed test input, which could be a step, a ramp, or parabolic. And we're doing that test from some time t. It could be at time 0, or it could be at some time during the particular processing of the control system, through to maybe infinity, or obviously it could be continuous like that, or it could be at some predetermined cutoff time. Now, steady state error arises from non-linear sources, for example, backlash in gears in a mechanical system, the configuration of the system itself, so it may be the physical setup, like a conveyor belt or something like that. It may not be the most efficient setup. There could be just, again, maintenance issues in electrical setup or electronic setup. It might be that the configuration system could be more efficiently done, for argument's sake, compared to what you currently have as a system. And the type of the input, of course. So sometimes the input is live, coming from the transducer, or it could be maybe stored data that's offline, so therefore then you're processing it, so the input could be quite different. Now, there are a range of test inputs, as we said: step, ramp, and parabolic or parabola, and these are used to assist in assessing the steady state error of position control systems. All right, let's consider a unity feedback system. As you can see there, we've got an input of R of S, an output C of S, and therefore our transfer function T of S will equal the output over the input, C of S over R of S. So we can rearrange that to find an expression for the output, C of S, which equals RS times T of S. Now, also the difference in the signal, we can calculate, as we see up here, E of S, so that's going to be the difference between the input and the output. And therefore we've already got a little expression for the output, and then we can see that we can derive a little equation for this difference in the signal. Now, we're interested in the final value of the error, so the error at infinity if you wish. So we're able to take the limit of that particular error function over time, and if we look at some mathematics, the final value theorem, we're able to find that that's the limit as s tends to 0 of s times E of S, and E of S we just finished deriving that R of S into 1 minus T of S, and therefore then, as we can see overall with that final value theorem, we're going to find that our final value of the error is the limit as s tends to 0 for s times R of S, the input function, multiplied by 1 minus T of S, the transfer function. So if we consider the steady state error in terms of that transfer function, again, we've got this input of R of S, we've got some difference occurring with the E of S, as we saw. The G of S is a transfer function, and output is C of S. So again, if we go through the process like we've done beforehand, we can see that very, very quickly we can derive our little expression for our output from our transfer function. G of S is going to equal C of S over E of S, so rearrange that to find our function of E of S. So that's always the difference between the output and the input. So therefore then we can get that expression, rearrange, and we're going to find an expression here relating our output, input, and our transfer function. Then we apply our final value theorem as we've done up above. So it's just the limit as s tends to 0 of s times that E of S function. So we've got this little function now that looks like a feedback, typical feedback form. So when we find that limit, we'll see that we're able to tell some things about the steady state error. Now, if we can change the input function to RS, what effect will it have upon that equation E infinity? So in other words, here's our little E infinity formula, but remember we said that we can change our input, so therefore it could be a step input, a ramp, or parabolic, for argument's sake. So if we put in a step as the input, R of S, then as you can see, there's our expressions that we've derived. Our R of S is 1 on S, so we can take that through, do a bit of simplification, and take our limit overall, and then we're ending up with this expression if we have a step input. Now note that this limit as s tends to 0 of the transfer function G of S is defined as the DC gain of the forward transfer function. All right, so now we have a little expression if we know that our step or input is a step input, and then we've got a little expression for finding that steady state error. Now, what happens if it's a ramp input? Well, that's 1 over s squared, so exactly the same thing again. We're going to plug it into our a formula. Again, you can see that we can simplify that down a bit. And as you can see, as we do that and take the limit, we end up with that equals the limit as s tends to 0 with s times the transfer function g of s on the denominator, so 1 over that. Okay, parabolic input, that's 1 over s cubed, exactly the same process again. And again, these are just general forms. But we'll see that it now will be the limit as s tends to 0 of s squared times g of s, that transfer function. All right. This also takes into account a way to define the system, so we call it system type. So the three terms in the denominator of the step, ramp, and parabolic functions that are taken to the limit determine the steady state error. These limits are called static error constants. So we can have the position constant, kp, equals the limit as s tends to 0 of g of s, the transfer function. The velocity constant, kv, which equals the limit as s tends to 0 of s times g of s, which is the transfer function, or the acceleration constant, k subscript a, which equals the limit as s tends to 0 of s squared times the transfer function g of s. Now, depending upon the values of g of s, these constants can have a value of 0, finite, be a finite constant, or infinity. And since the static error constants are in the denominator of the steady state error, then the value of the steady state error decreases as the static error constant increases. In other words, these are all in the denominator. Look at that last one. Since that's on the denominator, then obviously as this gets bigger, then overall that error from the parabolic input will get smaller. Likewise with the position, that being on the denominator, and likewise for that velocity constant, since that's on the denominator, overall that steady state error we'll basically get this. So how do we go about defining the system type? Well, again, sometimes we use this, sometimes we don't. Sometimes an equation will, a question will sort of say it's a type 1 situation, for argument's sake, or type 1 system. So this is how they go about doing it. So looking at the inputs, the steady state error formula, the static error constant, and the error. So for type 0s, as you can see, then for a step input, you're going to have this as your formula. You're going to have this as your static constant, and this static error constant, and also this single over error. So when you get that kind of configuration, then that's a type 0 for a step input. Likewise, as I said beforehand, you might be told that you have a ramp input. It has this as the velocity static constant, and therefore then it has an error of 1 over kv. So that would be a type 1. So you might just be told that information. It's a type 1 system, so straight away you can look up your table and figure out, well, they're the inputs. They're the type of errors that I should be getting, either as a check or perhaps as a calculation. So the steady state error can be used to specify the steady state characteristics of control systems. Indeed, feedback control systems can be used to compensate for disturbances. So in other words, you're able to then predictively turn around and say, well, okay, it's a type 1 system. These are the typical things that are going to happen if I have a step input, a ramp input, or a parabolic input. So therefore, then you can design around that, or at least be quite conscious that once your system gets operating, they're the typical outputs that you're going to get for whatever configuration that we're talking about. All right, let's have a look at the example. Still using a unit feedback system. Here our transfer function is given by k into s plus alpha divided by s plus beta squared. Now, it's designed to meet the following specifications. The steady state error, now for a unit step input, we've got to keep track of what kind of input we've got. So the steady state error for that unit step input is going to be 0.1. We've got a damping ratio for this particular control system of 0.5, a natural frequency of the square root of 10, and we want to determine k, the gain, alpha, and beta values. So let's look at what we know and what we don't know. Requirements for our design are that the steady state error is equal to 0.1 for a unit step. The damping ratio, as we said, is 0.5, and the natural frequency is the square root of 10. So finding the transfer function, well, that's just the output of the input. We're told that it's a unity feedback system, so therefore then straight away we can go to that unity feedback form, where obviously this is g of s times h of s, and h of s equals 1. Now, all we got to do is basically get a common denominator and simplify that. So just some basic algebra. When we do that, we'll end up with this particular expression, keeping in mind that this takes into account the unity feedback. We're always interested in the denominator because that's our characteristic equation. So here our characteristic equation is s squared plus 2 beta plus k times s plus beta squared plus k alpha. So therefore then that characteristic equation is very, very useful. We know that's in the form of, remember we've been talking about the modeling of control systems. And typically what happens is that for introductory courses, we try to get that back to a second order system. So this is a quadratic or a second order system. So therefore then we can straight away start doing some comparisons. So we know that the natural frequency squared is going to equal that last term. So straight away we can start generating little expressions. Plug in our particular numerical values. So now we have one equation. Now remember, we've got three unknowns. We've got the gain, we've got alpha and beta. So we're going to obviously end up needing to generate three equations. Likewise, we know that from definition that the damping ratio equals A divided by 2 times the natural frequency. So we can plug those values in and get a second expression. Likewise, we can start looking at, we know that we're talking about position static error. So we can use this formula, plug in our known values at the moment, and again end up with an expression. We know from definition that for this particular type of system, that the error is going to equal 1 divided by 1 plus Kp. Well, we've already figured out what Kp is from the expression just above. We also know that we want the steady state error with a step input to be 0.1. So again, we're just generating our equations. We can rearrange that, multiply through, and finally we've got our third expression. So now we're well on our way. So we just got to rearrange. In this case, I'm going to rearrange equation 3, this one. And what's that going to enable me to do is to go and substitute into my equation 1, because I've got K times alpha there. So therefore, when I do that, straight away I can calculate my beta value. And in actual fact, because it is a quadratic or a squared term, I can end up with 2 particular values. Now, as always, just because the mathematics tells you that there are 2 values, mathematically there might be 2 values, but in a physical context, that may not always be possible. So in this case, we're going to choose to substitute b equals plus 1, the positive one, and not the b equals negative 1 into equation 2, since b equals negative 1 will signify an unstable system. See what I mean? So therefore then, you know, the numbers do mean something, and sometimes it just demonstrates that there are physical aspects. In this case, beta equaling negative 1 will tell us it's unstable. And other times it will be just a meaningless piece of information that just won't work in the physical world. Mathematically it's correct, but the physical system just, you can't align it to that. But in this case, that's what the beta equals negative 1. So if we go about testing, first of all, beta equals positive 1, then as you can see, we can calculate our gain value. And when we do that, we end up with 1.1623. And you'll notice I tend to work to 4 decimal places. It's just a good rule of thumb. That way, you know, you can at least keep track of things, unless you're told that it has to be, you know, significant figures for argument's sake of a particular value. But it's just a good process. And also, if you do that when you're checking your answers against mine, then obviously we should pretty well match up without any sort of round off error as you're doing your calculations and checking them with mine. So now we know beta is going to be positive 1, and the gain k equals 1.1623. We can substitute in equation 3, and you can go out drops our alpha value. So we've already calculated all 3 values. So it's as easy as that. Now that's the steady state errors relating to the analog systems. What about discrete systems or digital systems? Well, as you might imagine, just like analog systems, digital systems can float about and therefore, you know, can have steady state errors introduced to them. So we're going to look at that. Here we're going to have a 0 order hold. So here's your typical feedback system. It's pretty typical of a, you know, basic control system. So we're going to deal with that, and what we can do is the digital computer is represented by that sampler, and also as you can see, the 0 order hold, and that's defined as always. Remember, there are other higher orders, but we're going to just, for an introductory unit, deal with the 0 order. So in that case, that's 1 minus e to the negative ts divided by s. So if we let g of s equal the product of those 2 things, the 0 order hold and the g1 of s, and we can use our block diagram reduction process for the digital system, then we're able to find a sampled error expression, which will be equal to E asterisk, which equals EZ, because we're working in the Z domain. So adding synchronous samplers at the input and the feedback, we obtain the following configuration. So that's, again, this is the typical process that you would use, the typical configuration. So once we go about looking and seeing that we can push the G of S into the unit sampler to the right plus the pickoff points, then you can yield that configuration. And again, stock standard, follow that process, and that would be the standard setup. Okay, now, if we use that original figure, we can convert each block to its Z transform to arrive at the following configuration. Great, so this looks familiar, of course. Exactly the same kind of idea that we've seen beforehand when we were looking at the analog systems. So again, as you might imagine, it parallels that, so it has a parallel form, except we're dealing with the Z domain. Likewise, we've got an expression here which will identify as a feedback system, but in the digital system, so nothing brand new there. Exactly the same thing, take the final value theorem for discrete signals, that will give you that expression or configuration. And then we can use the final feedback theorem on E of Z. We can determine that the sampled steady state error, E asterisk, because we're dealing with the Z domain, for unity negative feedback is of that form. And then all we're going to do is go through like we did beforehand. What happens if we change the input? Well, if we have a unit step input, we can see that a Z transform from this in the S domain will be equal to Z over Z minus 1. So we plug it into our formula, and lo and behold, oh, look, it looks very similar, doesn't it, to our analog processes. The unit ramp input, again, we've said beforehand in terms of the S domain, that's 1 over S squared. So the Z transform of that is going to be this form. Just got to look up your tables. And then you consider that into this formula. And then finally, we're going to result with E asterisk equals 1 over KV. So likewise with the parabolic one, we said that that's parabolic input, so therefore that's 1 on S cubed, so therefore the Z transform equals that, and we consider this process again, and the equations developed for the steady state errors for digital systems, as you might imagine, because it's steady state errors, we're just doing comparisons, they're similar to those developed for analog systems, whereas multiple pole placement at the origin of the S plane has reduced steady state error in analog systems. We can see that multiple pole placement at Z equal 1 reduces the steady state error to 0 for digital systems of the type discussed here. And this conclusion makes sense when one considers that S equals 0 maps into Z equals 1 and under Z equals T, E to the TS. Now again, don't get hung up on this stuff. Look at the formulas. There's some derivations there for you to take into account, but it's always the application of the mathematics. So why don't we have a look at an example? For a step, ramp, and parabolic input, find the steady state errors for the digital feedback system defined as follows. So as always, the configuration is that you have a 0 order hold cascading with that smaller function G1 of S. And in this case, G1 of S is equal to 10 divided by S into S plus 1. So when we cascade them together, as you can see there, we can simply take, keep this outside. That's a common term, it's just a constant, so we take the 10 all the way out, don't confuse it in any way, just put it at the front. And then of course we take the S squared into here, we'll take the S and there, it'll become S squared, so therefore then this is the process that we always use. We use a partial fraction expansion, and again that's your typical, you've got an S squared term multiplied by an S plus 1 factor, so when you do your partial fractions it's always your A term divided by S, B by S squared, and C divided by whatever factor it is. So in this case, it's S plus 1. So we go through, and what we're trying to do here is get a common denominator. And once we do that, we can see that the denominators are exactly the same. And what we can do is start playing around and looking at the coefficients in the numerator. So when we do that, the S squared terms, we can see that we don't have any S squareds in the numerator. So that's going to be 0 equals A plus C. So straight away we can get an expression for A. And if we look at the S1 terms, that's 0 again. There's no S1 terms. So that's 0 equals A plus B. So A equals negative B. And finally, S to the 0 equals 1, because that is the only value we've got on the numerator. And of course, anything to the 0, S to the 0 is 1. So therefore that equals the B term. So now we just do some basic algebra. We can rearrange our equations. Very simply come around getting the answer because we know B equals 1. So therefore A equals negative B, so A must equal negative 1. And of course C equals, as you can see, A equals negative C, so therefore then C must equal the negative of -1, which equals 1. Now these results in those calculations ends in a equals -1, b equals 1, and c equals 1. So we go back to our partial fraction, a general form, plug our values in, and as you can see, we can go through now, substitute those into a g of s term that we had beforehand, and just proceed by taking our z transform to, finally what we're trying to get is a g of z, of course, our transfer function in the z form. Go through, as you can see, just follow your z transforms, looking at your table, very basic. Follow that through, and as we can see, we're going to get a common factor here that we can multiply through by. So we do that, and that simplifies it a bit. So we end up with this expression here. Now, the key thing was that we also want to find out what happens for a step input, a ramp input, and for a parabolic input. So now that we've got that g of z, we can go through and test that, of course. So our kp is going to equal infinity when we plug all our values in and take our limit. And then we take the steady state error. Again, you can see straight away that's 1 divided by 1 plus kp from that little formula that we derived. And also for the ramp input, kv equals 1 on t into that expression. Likewise, as we go through, that's going to equal 10. And then our steady state error, looking at the final expression for a parabolic input, k of a, again, plug our values, and it's going to equal 0. So as we go through, as you can see, we end up with a way to go about calculating not only for analog systems, but for digital systems. And so as you can see, the answers obtained are the same as for an analog system. However, for digital systems, since stability depends upon the sampling interval, be sure to check the stability of the system after a sampling interval is established before making steady state error calculations. In other words, we want to make sure that your sampling rate is ensuring that the system is stable. Because otherwise, what's the point of taking steady state or trying to calculate steady state errors? You're wasting your time because the system will be unstable. All right, so as we say, steady state errors, you can find them for analog systems and also for digital systems. A couple of examples, and also you have some problems to work through and clarify some of the situations as well. Also, we said that we can define a type of system by looking at the way that we have particular inputs and seeing what happens with the steady state constants and defining the final output.